common data formats for the built environment. Before I jump into some of the lessons that I've learned over the years, I'd like to introduce myself. I only know a few people here in the room, so here is my background. I studied engineering science, focusing on civil engineering and structural engineering at the University of Toronto. And then I did a master's in earthquake engineering and engineering seismology at the University of Pavia and at the Université Joseph Fourier in Grenoble. After that, I spent about 10 years delivering structural engineering and multidisciplinary projects, many of which used parametric and BIM processes, and had a lot of fun and a fair amount of stress as well delivering those. And for the past 3 years, I've been gradually and have now completely made a career change to leading software development teams. So the 4 teams that I currently lead within Arup are Arup's team that deploys Speckle internally and contributes to its development. Arup Compute, which is a platform that allows our project teams and our skills networks to write calculations, store them in a centralized area, review them, and make them available, make the latest versions of them available within Grasshopper, within Excel, and within Python scripts. I also lead a team building a platform called Project Zero, which is collecting data on the embodied and operational carbon of all the projects we design across the firm. And I'm also the lead product manager for the Oasis Structural Suite, which includes GSA and AdSec and is our commercial structural analysis offering. And for the past year, I've also been a board member of BIM Quebec, which is a BuildingSMART affiliated group in the province of Quebec. At a high level, there's really 2 main sections that I have to share today. The first one is just my understanding of what is BIM. This is foundational to me in terms of how I understand BIM data formats and automation. So I'll just share that, and then I'll share a number of lessons learned from my years delivering projects and writing scripts on projects, and more recently, as I said, delivering software. So the first definition of BIM that I came across that really stuck with me and seemed to provide me with the intellectual rigor to actually organize my thoughts around BIM is given by Walter Dolezal in his PhD thesis of about 15 years ago. And it comes from the aerospace industry. I believe Dr. Dolezal still works at Airbus. And he said that a digital mock-up, which is their phrase for building information model, is a 3D representation of a project, so 3D geometry, along with its product structures and a bunch of attributes. And so as I look at that, the way I understand that, I take that to BIM and I say, okay, BIM is 3D geometry with attributes attached to that 3D geometry and a number of organizations, of structures of that geometry. And for me, the most important thing about this definition is that the structure, the way to organize the data, is plural. There's not just one, and we'll get into that later. So that's how I understand BIM. And so these are the areas of lessons learned that I'm going to go through. And for each of these, I'll share some of my thoughts, and I will also share some suggestions for what a data standard should or should not do. So there's no primary ordering. So the data that we talk about in a building is just things located in space. And there is no platonic data structure that is correct. Like I said before, when I was talking about the definition of BIM, there can be many, many structures. And so, for instance, the costing team might have one way of organizing all the data in a building. The design team has one way of organizing things. Who's designing what? The construction team has a very different way of organizing things. And so I think of an example where I had a senior engineer early in my career make a big point, putting a big note on the drawings that this sort of non-conventional item that we had on this project was supplied by Division 5, the steel fabricator, and installed by Division 3, the concrete fabricator. So this was something that existed, in a sense, in the hierarchy, in the structure, in two different places, depending on if it was the supply organization or the install organization. And of course, operators have their own structure as well, and they have completely different needs of the models. So there's a way the way I think about it is that the 3D geometry and the attributes present something absolute about the data, but the structure and the hierarchy and the organization of the data is a reflection of the needs of the person using the data. So the implications of this for a data standard is that the organization of the data should be independent of the definition of the data. We don't want to bake those two things together. We want to be able to have one definition of a beam. There's one beam, we define it once. However, that beam may exist in 18 different structures throughout the project. So having those independent allows us to have a fighting chance of helping to solve that problem. And obviously as well, the standard should allow multiple organizations on a single data set. And whether that is multiple organizations within of the same data set owned by all the same people, or whether the standard is may allow multiple people to own organizations and hierarchies of one data set. I don't have the answer to that, but there are multiple organizations of BIM data on projects, and that's a reality that the standard has to support. Secondly, it's important not to mix the definition and the organization. So there's two hierarchies of data. One is the definition hierarchy. So this is, for example, you have a building element, a constructed element, and then maybe a beam is a subclass of element, and Revit beam is a subclass of beam. If you'll pardon me for giving the specific example, this is something that we have within Speckle. So Speckle has this fairly shallow hierarchy of definition. And so it's something that is a general thing to a more specific description of the same thing. And this is the key thing. In a definition hierarchy, you say that a Revit beam is an element. So it's this is-a. And as you go down, you're always talking about the same thing, but you're talking about it in a more specific way. The hierarchy of organization, on the other hand, is something like project to building to floor to slab, and is really going from larger containers down to smaller containers down to individual things. This is the has a relationship. And we want these, it's very hard to accommodate both of these at the same time. And sometimes you have definitions of sort of references from one thing to another baked into the definition of a model, where you say, this beam has a reference to a floor, or a floor has a reference to all the beams in it. And these are situations where you can kind of get those two things together. So my suggestion is that, first of all, the definition hierarchies should be as shallow as possible. If you think about the sailing world, for instance, in terms of how they define things, everything has a really weird name, none of it makes any sense, and everybody understands it because they've been calling these things the same things for 500 years. And whether it's the jib or the mainsail or the I'm not a sailor, I apologize, but there's a vernacular vocabulary that exists, and that's sufficient for people to understand each other. So you don't need a deep definition hierarchy. The hierarchy of the definition doesn't need to tell us anything. We just need to agree on the name of the thing. And so having a shallow definition hierarchy allows people to work with it fairly easily, allows us to understand the standard very easily. and it is generally a fantastic thing. And secondly, we need to really be careful that the data structure doesn't impose any specific hierarchy of organization. So again, going back to the first point about the data structure is separate from the data definition itself. It's just something to keep an eye on. And finally, we want to be able to describe things outside of a hierarchy. It's nice to be able to just share snippets of information without always having that hierarchy in place, and trusting people to be able to communicate without necessarily all of that big burden. And of course, if the data format can do it, it means that it's simple and it's robust, and it doesn't necessarily mean that people will be doing that much. One of the things that I do as a team leader is trying to simplify things as much as possible. Simplify things down to what really needs to happen. Try to understand what the core of things are. And so over the years, geometry, time, and analysis are three areas where there's a lot of complexity that can sneak in. So I'll just share a few thoughts on each of those. So I don't have a huge amount to say about geometry. I certainly don't have strong opinions about geometry. These are some of the questions that I think are important to ask. So primitives, B-reps, or meshes for geometry. There are situations where each of these, depending on the situation, is the best solution. So there are times when we want primitives, sometimes we want meshes, and sometimes B-reps are, how can you live without B-reps? Should the standard include support for parametric definitions? I don't think it's a given. I think there's a lot of value in a standard that provides a baked-in geometry, so to speak. And another question is, should a BIM model at a technical level store attributes on geometry? And this is very simple. You just have a bunch of geometric objects and you attach attributes to them. Or do we have a set of objects that have a geometric attribute? And this makes it easy to attach multiple geometries to a single object. So you could have a high and a low resolution geometry baked into an object. You can have a specific baked in mesh, but also include the parametric definition. I'm not sure what the answer is on all this. For myself, my view is that the geometry has to be expressive, it has to be powerful, and it has to be unambiguous. For those of you who have worked with arcs, everybody has their own way of defining arcs. It's really annoying. The standard should just have one way of defining one kind of geometry. End of story. We sort that out, and life is good. Time. So when dealing with time, it's best to start with a clean snapshot. So although data structures, the data we're showing, and the processes that use them and modify them are closely related, they are distinct. Time-varying properties and the tracking of design revisions are a complex problem in their own right. It's a big issue. If you look at the software industry, they spent a lot of years dealing with the time-varying nature of their code bases, and they've got some very robust solutions. So when we come to defining a standard, my personal view right now is that the data standard, the data structure, should exclude any and all mechanisms for tracking revision history. Just don't. It's a big problem. There are solutions. What the standard should do is allow the differences between two versions of a data set to be automatically detected. So if you can get automatic change detection and you can provide a meaningful display of what's different between two versions of the same file, then there's a whole world of existing tracking tools that can come and that can support the robust and the reliable tracking of data. But getting that into the data set, I'm not sold. Finally, the last area of complexity. I'm a structural engineer. I lead a team that writes structural analysis software, so I think a lot about this. And analytical models are very different from a BIM model in that they do have an inherent topology. There is a connectedness to it. There is an organization, so to speak, because that's what you're looking at. You're looking at the flow of energy, or you're looking at the flow of forces through a structure. So there is that inherent topology that's quite different. And when it comes down to it, they have geometry, but they're not really geometric models. They're mathematical models. They they reduce to a set of equations. So when it comes to looking at a standard for BIM data and showing that BIM data, there's not a lot of value, or rather there's a danger, I think, in introducing complexity into the standard for the sake of accommodating analytical models. So if you want to keep the scope simple, focus on modeling and describing the physical shape of a building. There's a lot of initiatives in the structural world for model sharing. I think I went through the open standards for structural model sharing sometime last year, and there were 5 of them that were fairly well established. There's I think it's GBXML is a very established format for energy models. So those are very different problems to BIM, and so there's not a huge amount of we should be concerned about adding complexity in for the sake of accommodating those. And the final thing is, why do we standardize? And so here we've got a spoken hub model and a point-to-point model. And I'm not talking about how data flows from one person to another. How do we send it to a server? Do we send someone an email? Do we send someone, do we put something on the architect's FTP? That's not what we want to, or not what I'm trying to discuss here. But it's this idea of, how do I get the information in a way that other people can understand? And so if there is a common language that everybody speaks, right, and everybody to communicate with others only needs to learn that one common language and doesn't need to think about how other people understand or speak that common language, then the math is very simple. Everybody needs to learn to read and write that standard. And if there are 20 people doing it, or 20 programs doing it, or there are 80,000, everyone still needs to read and write 2 languages. The point-to-point model does not scale, and we know that's important. However, the thing is I've seen this in, sometimes there's a need for expediency, and we're trying to build something quickly. We add something to the standard, and everyone sort of has their own different implementation of the standard, and then all of a sudden we do need to care about everybody, even though we are using a standard. So it's not an either or, there's a slippery slope between them. So it's really important that for a standard to be scalable, it needs to be both simple, that everyone can learn it, and also very strict. The standard needs to make decisions, not provide choices. So, in this sense, a standard that's hard to write, right, where we actually do the work of making decisions and getting agreement on what we're going to call things and how we're going to describe things, becomes a standard that's easy to implement. And so the value I see in standardization is scaling, getting more people involved. I know I've seen a lot of excitement around IFC.js recently, which is making IFC accessible to many people, and it's got this promise that I think is really wonderful about, hey, just deal with this package, just deal with this standard, and you'll be working on things that anybody can bring into their workflow, and you'll be able to collaborate with everyone. So to summarize, the lessons that I've learned over the years is that there's no primary ordering in a BIM model. It just is in space, and the organizations and the orderings are a reflection of the person looking at it, not something inherent in it itself. it's important to keep the definition and the hierarchy of definition and the hierarchy of organization separate. They are separate things. One, we want to be simple, and the other one, for anyone who's spent any time with Uniclass or master format or its equivalents, knows that the hierarchy of organization can be very, very, very complex. To simplify the scope, to make things, which is just to make things more powerful and work better, 3 areas to look at are geometry, time aspects, stepping away from that as much as possible, and just understanding the differences between BIM and analytical models. And the last point, again, is the reason we standardize is to scale, which means that the standard really needs to make decisions. It needs to be something consistent that everyone can use. And yeah, that's it. Thank you very much.